let us start with our first speaker, Aleksi Vuorinen, who's very well known in that field. And I give him the word and ask him to share his screen with his slides. So his slides are also already for download on the website.
Okay, thank you very much, David, and good morning to everyone from Helsinki. So I'm very pleased to present our recent work done together with Emily Annala, Tyler Goda, Aleksi Vuorinen, and Joonas Nättilä on a model-independent interpolation of the neutron-star-matter equation of state and its implications to the existence of matter inside massive neutron stars that perhaps will turn out to have similarities to what we expect from deconfined quark matter. Now in a talk on this topic, it's of course almost mandatory to start from the QCD phase diagram, since after all this is the quantity we are very much interested in mapping. This is the motivation for our work. Already yesterday we saw many impressive talks that mainly concerned about the sort of high temperature part of this phase diagram, where we have both very nice experimental and theoretical tools at our disposal to describe the system. We have heavy ion collisions that we can analyze in a laboratory, and we have lattice Monte Carlo simulations that provide a robust non-perturbative first principles tool to study the properties of hot quark-gluon plasma and the transition from a hadron gas to the quark-gluon plasma phase. But now today our attention will be shifted to another part of this phase diagram, to much colder and much more dense systems, where first of all we don't have lattice QCD at our disposal because of the sign problem, and second, our laboratories are kind of inconveniently located very far away from us as neutron stars. Now when we go to neutron star physics, I would claim that the underlying question, or the main question we are addressing here, or at least I will be addressing in my talk, is whether we can determine the properties of the cold and dense matter, QCD matter, that neutron stars are composed of, using only really first principles quantum field theory tools, and on the other hand then robust astrophysical observations. So our observational data on the macroscopic properties of neutron stars. And now clearly here we are dealing with two very different types of physical things on one, or scales. On one hand, the microscopic scale, that somehow where interactions, QCD interactions, determine the thermodynamic properties of this QCD matter, and then on the other hand, the macroscopic properties of neutron stars, their masses, radii, and so on. And as you all know, the connection between these macroscopic and microscopic worlds is provided by the famous TOV equations that basically connect the equation of state, the functional relationship between the energy density and pressure of QCD matter, to the macroscopic properties of neutron stars, mainly their mass radius relation. And the way this works is that if we have an accurate understanding or information on the equation of state, then by plugging that into these TOV equations for non-rotating stars, we obtain an accurate, precise prediction for the mass radius relation of neutron stars, on top of which all of our observations should collapse on. Now, of course, the reality is much more complicated, and the theoretical predictions for the equation of state from nuclear theory and the corresponding mass radius relations have not really converged on one single curve, but they are kind of all over the place. They may be precise in themselves, in the sense that the calculation is sort of doesn't have numerical uncertainties, but then there are clearly some underlying theoretical uncertainties that lead to this present situation, where we don't really have an accurate understanding of what's going on. And I would at least claim that this figure alone really motivates well the clear need that we have for a systematic and model independent approach to the microphysics of neutron stars, and thereby also to the prediction of the macroscopic properties of these objects. But to get to answering at least partially this question, let us start from what we robustly know from purely theoretical tools. So what do we know about the neutron-star-matter equation of state? So here, what I think is accepted by more or less everyone is that the low density side of the equation of state is by now rather accurately known. On one hand, from things like potential models that are very tightly constrained, and on the other hand, then from the impressive use of effective field theory methods in nuclear theory, in particular the chiral effective theory. So these kinds of tools have given us or provided us with accurate information on the neutron-star-matter equation of state, here shown as the pressure of beta-equilibrated zero temperature neutron star matter as a function of the quark chemical potential, offset by 1/3 of that corresponding to iron 56. And what we see here is that we have a very accurate prediction up to densities of the order of the nuclear saturation density, where the current errors are perhaps of the order of plus minus 20% or so. There are some groups that have gone even further, even to 2 saturation densities, but to be very conservative, I'm going to only be using these results from the group of Achim Schwenk that go up to 1.1 saturation densities. Now, fortunately, this is not everything we know about QCD and QCD matter. We also know that QCD is an asymptotically free theory. We know that this curve here should at some point asymptotically approach a curve given by a very simple calculation in particle theory, a calculation that deals with a system of free non-interacting quarks. But of course, this is not enough for any practical purposes in neutron star physics, because it's not enough to know where this curve should asymptotically go to, but we need to know how fast it approaches this asymptotic limit. And here one might first sort of naively think that starting from the high density side using weak coupling techniques might not give us very much, because clearly at the interesting densities here, where we are sort of talking about the interiors of neutron stars, the system is far away from being a sort of weakly coupled system of almost free quarks. But nevertheless, the application of perturbation theory starting from the weak interaction side does give us something very useful. It basically gives us the equation of state down to densities of the order of 30, 40 saturation densities or so, with similar uncertainties as what we have seen in the CET equation of state at densities of the order of 1 nuclear saturation density. And here the main uncertainty in the perturbative equation of state comes from the renormalization scale dependence of the result, which is something that we are very much working on diminishing with people like Tyler Gord and Aleksi Vuorinen and Saga Sappi. Now, the way I would somehow summarize the current situation, forgetting all these details about the microscopic calculations, is that we have accurate theoretical understanding of the behavior of the equation of state at low densities up to roughly the nuclear matter saturation density, and at very high densities down to something like maybe 40 saturation densities. But in between, we have a fairly wide no man's land where we can either use different model calculations or maybe, if we are bold, use some novel non-perturbative techniques like the ADS-CFT correspondence, or what I'm going to be discussing in my talk today, a model-independent approach that doesn't take advantage of any other theoretical microscopic information than what you can see in this figure, and then where we simply interpolate the equation of state in between these limits, and then allowing the equation of state to behave in any physically reasonable way possible, we try to constrain its behavior with observational data. Now, to get here, we of course have to say also something about what we know from observations. What are the robust data points that we can use to really constrain this equation of state? Now, here the maybe most fundamental quantity on which we have the most information available are the masses of neutron stars. And here a particularly important data point is what is the mass of the most massive neutron star for which we have a precise mass determination. And at the moment, roughly speaking, this value is somewhere around 2 solar masses. There have been some recent indications of neutron stars with masses that probably even exceed the 2 solar mass limit, but we are still, to be conservative, we are still waiting for the final word on the fate of the error bars in those cases. But what we can say very robustly right now is that there exist 2 solar mass stars. What this means is that we know that the maximal mass, so basically the point where the neutron star mass radius relation ends on this MR plane, has to reach this horizontal red line at 2 solar masses, and we can immediately discard all of those EOSs which do not reach this red horizontal line. Very good. Now the neutron star radius is then another very important and interesting quantity, but for technical reasons, we don't have quite as high quality data as for the mass itself. So current simultaneous mass radius measurements have 1 sigma error bars or uncertainties that are typically in the range of several hundred meters, plus minus several hundred meters. So nowadays, I think it's fair to say that we know that it's very likely that the ballpark where neutron star radii land at is in the say in the ballpark between 11.5 and 13.5 kilometers or so, but this is maybe not at the level yet where we could use these results as input in calculations of the type that I'm describing. But then fortunately there is a third type of observation coming from the famous gravitational wave observation from neutron star mergers, the first one seen by LIGO and Virgo already in 2017, which provides us with input concerning the tidal deformabilities of neutron stars. Then there's some information from the electromagnetic counterparts of this one particular gravitational wave event, and hopefully in the future we will also have information on the ring down pattern in the gravitational waveform. Now, from all of these different inputs, the one that I'm going to be using in the calculations that I'm discussing today are these tidal deformability bounds, and they really concern the values of one single parameter that basically tells us how the sort of form of a given neutron star reacts to an external quadrupolar gravitational field. Basically, this tells us what kind of a quadrupolar component our star's gravitational field develops when the star is immersed in an external quadrupolar field. Now, simulations of neutron star mergers have shown us that non-zero values of this lambda parameter have a substantial effect on the gravitational waveform that's created, and LIGO and Virgo have been able to place very, very useful bounds on this quantity that can be given in terms of a bound for the tidal deformability of a 1.4 solar mass star. We know that with 90% credence, this quantity is between the values of 70 and 580, and this is very useful because for any interpolated equation of state, we can determine this value, the tidal deformability of a 1.4 solar mass star, fairly easily, and then discard those EOSs that do not fulfill this requirement. So very good. Let us now then finally at that halfway point more or less of my talk get to this interpolation topic. So how do we optimally combine all these theoretical and observational insights that I have been informing you about so far? Now, in a nutshell, the idea in this interpolation approach is that we take the low density and high density limits of the equation of state sort of at face value. We take these as given to us by these microscopic calculations, and then we divide the density regime in between these two limits, this no man's land, to several pieces, and we use some kinds of interpolating functions to sort of fill this no man's land, requiring a couple of physical constraints. So first of all, we of course require that our interpolating functions smoothly connect to the low density and the high density limits, because we do not expect physical phase transitions at these points. Then we demand that the pressure and number density are both continuous functions. The number density is allowed to jump in exactly one point, which would correspond to a first order phase transition. We also require that the speed of sound remains below 1, and optionally, once we have generated large ensembles of viable neutron-star-matter equations of state, we can then use astrophysical constraints to discriminate between individual EOSs. So to give you a first flavor of what the results of such interpolation calculations might look like, here this cyan cloud represents the outcome of the generation of about 200,000 viable neutron-star-matter equations of state in the form of 4-part polytropes that we generated for this 2018 PRL. And this cyan region for the EOS translates to a very, very large mass radius cloud. Now we can additionally then constrain this EOS and MR cloud by taking into account first the existence of 2 solar mass stars, which rules out clearly this bunch of mass radius relations which do not reach this 2 solar mass limit, and this then simultaneously excludes a bunch of equations of state that are simply too soft at low densities, and here we also end up ruling out neutron star radii that are for 1.4 solar mass stars are roughly less than 10 kilometers or so. Then we can take advantage of this tidal deformability measurement of LIGO and Virgo that turns out to take out a chunk of MR relations that would predict very large maximal neutron star masses and neutron star radii, and that then in terms of the equation of state corresponds to ruling out equations of state that are basically too hard, too stiff at low densities, because these would lead to neutron stars with very large radii. Now this basically gives us that the radius of a 1.4 solar mass neutron star is very likely less than about 13 kilometers. And finally, we can play sort of speculative games with radius measurements. For instance, if this one particular X-ray measurement that I showed you, I flashed you before, that was in terms of radii 12.4 plus minus 0.4 kilometers, if we happen to know accurately the mass of that particular neutron star, that it was 1.9 solar masses, which we actually don't know, that's why this is a very speculative calculation, then we would again be able to throw out quite a chunk of both equations of state and mass radius relations. So this is, roughly speaking, the typical outcome of a sort of an interpolation calculation, the types of interpolation calculations we have been performing. But now one can of course ask the question, can this kind of an interpolation approach tell us anything about the physical phase of QCD matter inside neutron stars? And this brings me finally to this relatively recent work that was published in Nature Physics earlier this year, where we did an interpolation calculation starting not from the equation of state itself, but from the speed of sound. Well, why we did this was basically because this allows us to classify our results in terms of the maximal value that the speed of sound reaches, and also in terms of the latent heat of the deconfinement transition. Now you might ask, why are we interested in the speed of sound of neutron star matter? In a nutshell, we are interested in it because there's a tension between somehow the standard law in nuclear theory that suggests that the speed of sound very likely obtains very large values, even close to the speed of light, and what we know from different other physical systems, for instance, high temperature quark-gluon plasma, where we know that even the conformal limit of the speed of sound being 1 over square root of 3 is actually never reached. And this limit is very difficult to break even in sort of purely theoretical setups, for instance, in using the ADS-CFT correspondence. And some people have even sort of entertained the idea that this conformal speed of sound, c over square root of 3, might be some kind of a universal speed limit that no physical system can ever exceed. This is by no means proven, and there are some example systems, for instance, QCD at finite isospin density, where this speed limit is in principle exceeded, but nevertheless, it seems that nature has a hard time of producing speeds of sound that go above this limit. Now, if we do indeed this interpolation starting from the speed of sound, what we then end up with is an equation of state plot that looks very much like what I showed you previously, with the exception that we can now ask questions like, what would the band of equations of state be if we knew that the speed of sound squared never went above, for instance, 1 over 3 or 0.4 or 0.6. This is what we can see from here. Now, the form of this EOS band is very interesting, I would say. For one thing, what especially this low speed of sound bands suggest is that we could it almost looks like we could just take a ruler and continue the CET EOS from low densities upwards, and on the other hand, this PQCD EOS from high densities downwards, and then they would meet somewhere around here where there's a visible kink in this EOS band. So this maybe at some level suggests that there might be some kind of a phase transition going on where in the region where there's a kink in this plot. And this suggestion is even further strengthened by the observation that if we plot here nuclear matter, nuclear theory EOSs that extend beyond this 1.1 saturation densities, they really continue on an almost straight line to higher densities. And the distinguishing feature between these EOSs and the PQCD EOS that you can sort of extrapolate from high densities is clearly in the value of this logarithmic derivative of the pressure with respect to the energy density, the polytropic index gamma that obtains the value of roughly 2.5 at low densities and 1 at high densities. So now there are some obvious questions. One can ask, is this two-slope structure only a property of these bands, or does this observation persist differentially when we look at each EOS at a time? And also, of course, it's a very interesting question to ask, where do the centers of different types of neutron stars lie in this plot? Do they lie to the left of the kink, suggesting that there's no quark matter inside these stars, or to the right of the kink, suggesting that there actually might be quark matter inside them? To investigate this question, we generated a large ensemble of viable EOSs with this technique, allowing for arbitrarily large first-order transitions, and then we compared the behavior of 3 physical quantities: the polytropic index, the speed of sound, and the pressure divided by the pressure of a free system of quarks to sort of differentiate between the behavior of our interpolated equations of state and the hadronic equations of state that we obtain from the literature, and that are viable in the sense that they are in agreement with all the astrophysical observations. And now I'm going to show you results from this kind of a comparison calculation with these black lines standing for the nuclear theory EOSs, and this blue line here standing for the PQCD limit, where we know that our interpolated EOSs should eventually reach. Now, the first thing I will do is I will mark here with these cyan and red circles and diamonds the locations of 1.4 solar mass stars and maximal mass neutron stars, where their centers lie on these EOS lines. Now, if we add here our interpolated equations of states as these thin gray lines, we see that some of them clearly follow these nuclear theory curves quite a long way, but then eventually they all end up at this PQCD limit. But what is even more interesting is where do the centers of 1.4 solar mass stars and maximal mass neutron stars lie? it turns out that the 1.4 solar mass stars lie in this regime, which has a very nice overlap with the nuclear theory predictions, but then the maximal star centers lie somewhere much closer to the PQCD limit than to the centers of these purely nuclear matter stars. And this observation can be taken also to these 2D plots that show projections of the 3D plot that clearly shows that for maximal mass neutron stars, there's almost zero overlap between the centers of our interpolated stars or neutron stars built from our interpolated EOSs and the group of these neutron stars that are completely hadronic. Now, if we went one step further and introduced, just as a guiding principle, a horizontal line at gamma equals 1.75, exactly in between the PQCD limit for gamma and the CET limit for this quantity, to differentiate between quark matter and nuclear matter, then this would allow us to ask questions about the presence of quark matter inside neutron stars of different masses. And in short, our conclusion is that if the purely hadronic neutron stars are only possible if simultaneously the speed of sound reaches very large values, CS squared goes above 0.7, and the phase transition is fairly strongly first order. Okay. Otherwise, quark cores are inevitable. And I'm now coming to the end of my talk. The last slide I'm going to show you is a comparison with sort of less robust measurements. I will just note that our results are perfectly compatible also with recent radius measurements, and also with the suggestions that the neutron star maximal mass might be below a sort of number of the order of 2.17 solar masses. Thank you very much. I will leave you with these conclusions that I clearly don't have time to read aloud. Thanks.
Thank you very much, Aleksi. So indeed, we have almost used up the time, but we started a bit later. So please, questions, urgent questions. Now we have the discussion session at the end of our session. So please, I'm sure there are some questions. I always had such a question, maybe you can immediately clarify. There was a statement that according to this conformal limit, that the approach to the conformal limit, to the asymptotic freedom limit, should be from below. Actually, yes. What approach is from below? Pressure versus chemical potential, or what approach?
No, the speed of sound approaches from below. Okay. This is actually given by just the sign of the beta function. So this is a robust result. This just tells us that if you compute the speed of sound perturbatively, then the sort of at infinite density or zero coupling, the limit is exactly this 1 over square root of 3. But then the leading correction, this result comes with a negative sign, meaning that somehow if you look at very, very high densities, then the speed of sound approaches this limit from below.
Mm-hmm. So
there might have been a question in the chat.
Okay, so yeah, Veronica, would you like to speak? Pronounce your question.
Thanks, David. Thanks, Aleksi, for the nice talk. I have a question concerning that plot that you showed from the Nature paper, that you can clearly see those lines looking like there's a first order phase transition.
Which one do you?
Yeah, or maybe a few earlier. Yeah, that one. Oh yeah, that one that you showed the two lines crossing.
Okay, yeah.
Do you have a version of this plot that's not log scale? Just because I have a lot of trouble, getting information from log plots. Somehow my brain doesn't work that way.
I'm not sure if we have actually produced one like that. We can, if you want, we can certainly do this. So I should really emphasize that what we have done here is a truly trivial thing. This is only to sort of to guide the eye. That if you really looked at this basically the purpose of these lines is to ask the question, what would happen if you blindly extrapolated from very low densities and from very high densities using the slopes that we obtain in those limits, and then we would obtain this kind of a sharp kink roughly here, but this is clearly not what we somehow predict. We don't actually, our prediction is just that the equation of state is somewhere inside this band. We certainly don't advocate this kind of a sort of sharp behavior, but it's somehow amusing to see that this kind of a truly trivial extrapolation would lead us to something that is probably not terribly far from somehow reality.
Okay, Veronica, we will come back to exactly this plot more in the discussion. So please come back also in the discussion, then we can have a more detailed discussion. At this point, I would like to point out what Roman also is writing now in the chat. Whoever wants to raise a question should press this raise hand button, and we will follow. Now, for the moment, we have used up the time. We will have the long discussion after the whole session, and let us thank Aleksi for the very, very nice talk.